So this video is going to talk about how we can infer certain information about a function based on information about its derivative. So here on the left-hand side is characteristics of some function f, and then what I want to do is kind of show you what we're looking for in terms of the derivative to evaluate these characteristics on the left. So for example, if a function is increasing, that means the first derivative has to be positive. If a function is decreasing, that means the first derivative is negative, because remember the derivative represents the slope of a function. If there's a minimum, I'm going to specify and call this a relative minimum. That means the derivative f prime of x goes from a negative value to a positive value. If there's a maximum, again, relative, that means f prime goes from positive to negative. A point of inflection occurs when the second derivative changes sign. Okay, not just when the second derivative is equal to 0. For the point of inflection to occur, there has to actually be a sign switch of the second derivative. And then function is concave up if the second derivative is, right over here, if the second derivative is greater than 0. Or the second derivative with respect to x is greater than 0, and then it's concave down if the second derivative with respect to x is less than 0. So this is kind of just a summary of all of the questions we're going to see that involve graphical analysis. So this is a good thing to have in your notes and refer back to if you're asked a certain question about where a function is concave up, where it's concave down, etc. So I'm going to go through two, an example and then a practice question that are very similar, and then a problem set that's a little bit more challenging. So pretty typical question is you're given a function, in this case we're just given f, and we want to determine the interval or intervals where the function is increasing and decreasing. So that is an indication that we're going to be dealing with the first derivative. So the first thing we're going to do here is take this function and then identify the first derivative of it. So the first derivative is 3x squared plus 6x minus 24. And then the way this kind of works is we're going to set this equal to 0. And then we're going to determine the intervals where this function here, the first derivative, is positive, and where it's negative, because that will tell us the intervals where the original function is increasing and decreasing. So to do that, I'm going to factor out a 3. And this is actually factorable, so let's factor this again. So to define the actual interval, we're going to make a number line that have the critical points on them. The critical points are the location points where the first derivative is 0 or undefined. In this case, those are going to be -4 and 2. And the basic idea here is we just want to determine whether or not the first derivative is positive or negative in each of these different segments. So let's start with I think the middle is usually a good spot to start if the middle is 0. If we plug in 0 here into this function, we get a value that is negative. So this is negative here. If we plug in a value that's less than -4, let's take -5. Well, this will be negative. This will also be negative, so this is positive. And now let's plug in +3, a number that's greater than 2. Well, this is going to be positive. This is going to be positive, so this is positive here. So the intervals where the first derivative is positive are going to be the intervals where the original function is increasing. So that is going to be -∞ to -4, and then 2 to infinity. The interval where the first derivative is negative is going to be the interval where the original function is decreasing, and that's going to be -4 to 2 in this case. So those are the two answers for the first question. This number line is also useful because it will tell us where the relative max and relative minimum values are, which is our second question. So the relative max occurs when the first derivative goes from a positive value to a negative value, and that is going to occur at -4 here. So if we imagine the original function will look something like this, and if we write it like this, clearly there's going to be a relative maximum at -4. The relative minimum will occur when the first derivative goes from negative to positive. In this case, it's going to occur at 2. And so that's our answer for the second question. Part C wants us to find the interval or intervals where the function's concave up. So this, if the first derivative is 3x squared plus 6x minus 24, then the second derivative is going to be 6x plus 6. And what we're going to do here is set this equal to 0 and then find the potential point of inflection. Just because a function, the second derivative is equal to 0, doesn't mean that the point of inflection is going to occur there. We need to prove that the sign of the second derivative is actually changing. So -1 is going to be what we're going to check. So let's pick a value less than -1, which is, let's pick 0. So we get our less than -1 would be -2. So let's pick -2. We get negative. Now pick a number greater than -1. Let's pick 0 for that one. That's going to be positive. So this is concave up on the interval -1 to infinity. So the number line's a good technique because it allows you to kind of answer a lot of different questions, but with just referencing kind of one figure. Let's go through a very similar question. So practice. If I have a function defined as the following, let's determine where it's increasing, decreasing. Let's start there, and then we'll work on to part B. So in this case, here's our function. And we're going to find the first derivative. So you get 3x squared plus 3x minus 18. Similar with the last question, we're going to set this equal to 0, and then determine the intervals where it's positive and negative. So this is equal to 0. Let's factor out a 3. And now let's factor this again. And so this is going to give us the 2 critical points, which we're going to use to find the intervals. So the first critical point is going to be -3, and the second one is 2. Let's plug 0 in the middle. We get negative. If we plug a value less than -3, we get a positive value. Value greater than 2 is also positive. And so the original function will look something like this. So the original function will be increasing on the interval -infinity to -3, 2 to infinity. Because the first derivative is positive, it will be decreasing on the interval -3 to 2 because the first derivative is negative. When it says classify the relative extrema, that just means find the relative max and relative min. The relative max will occur when the first derivative goes from positive to negative. So that's going to be at x equals -3. and then the relative min will occur when the first derivative goes from negative to positive, so it's x equals 2. Okay, then lastly, let's find the interval where the function is concave down. So once again, we're going to start with the first derivative, and then when we're talking about concavity, we want the sign of the second derivative. So we're going to take the derivative of the derivative. So this is 6x plus 3 equals 0. There's a few different ways we could solve this. I'm going to factor out a 3. And so the potential point of inflection here is going to be at negative 1/2. And if we pick a value less than negative 1/2, this becomes negative. If we were to pick like negative 4. And then if we picked a value that's greater than negative 1/2, let's pick 0, we get a positive value. So we want to figure out the interval where it's concave down. And so that's going to be from negative infinity to negative 1/2. Okay, so those two examples are very similar. Let's go through one that's a little bit more challenging because the way we're given information is a little bit different than the last two questions. So problem set number 1. So here we have, instead of giving the original function, this question gives us the graph of the derivative. But we're essentially being asked the same questions as we were before. So here we have the graph of the derivative defined from negative 5 to 5. And it just talks about how it's semicircles and line segments. What we want to do for the first question is determine where the function f has a relative maximum. So where does f, well, if we want to figure out where f has a relative maximum, we want to figure out where f prime goes from positive to negative. Because if the derivative goes from a positive value to a negative value, then the original function will have a relative maximum. And so we're going to look at this graph and determine where the y values go from a positive value to a negative value. So anything above up here is positive, anything below is negative. So there are 2 points where the graph of the derivative goes from positive to negative, and that's going to be at negative 3, and then the other one is at 4. And so the two values where the graph of f goes from increasing to decreasing, meaning the graph of the derivative goes from positive to negative, meaning that we have a relative maximum, these are going to be at x equals negative 3 and x equals 4. Okay, similarly, if we want to find where f has a point of inflection, we want to determine where does the slope of f prime, which is really equal to the sine of f double prime. So where does the slope of f prime change signs? So where does the slope of f prime change signs? In other words, where does f prime go from either decreasing to increasing or increasing to decreasing? So it's going to be here. That's 1 point because it goes from increasing. F prime goes from increasing to decreasing. So x equals negative 4. Here's another point because f prime goes from decreasing to increasing. It's at negative 1. And then the last point is right here. Even though it's not differentiable here, the slope of f prime still changes, and therefore there is a sign change of f double prime, therefore there's a point of inflection. So x equals 2. So we want to figure out where f prime changes from increasing to decreasing or vice versa, which will tell us where f double prime is changing signs, which tells us where the point of inflection is located. Okay, so it's going to be these 3 points right here. All right, and then lastly is kind of a combination of the concepts in letter A and the concepts in letter B. We want to figure out where f is concave up but also has a positive slope. So we're concerned with f. We want to figure out where it has a positive slope. Well, it's the same thing as increasing. Okay. And concave up. So if f is concave, I'll start with increasing. If f is increasing, that means f prime is positive. Okay, so we're going to be concerned with all of the values of x where f prime is above the x-axis. So those are the two intervals we're going to be talking about. So -5 to -3, and then 1 to 4. We also want to figure out where it's concave up. Well, that's going to be where f double prime is positive, or where the slope of f is increasing. So this is going to give us another set of intervals, and then the idea behind this question is we're going to find where those intervals overlap. So in other words, it's going to be f will be concave up when f prime is increasing. So that is going to be here. It's increasing, it's going up from left to right. It's also going up from left to right here. These parts right here, these two segments. Okay, and so the overlap between these two is going to be our answer. And so that is going to be this right here, this part, because it's both positive and increasing. So -5 to -4. And it's also going to be both positive and increasing right here, which is 1 to 2. And so that's our answer for letter C.